Another way we analyze raster data is to classify or reclassify raster cells. In this case, we're going to classify raster cells with symbology, where we group cells by unique value or numeric range. And if you look at the examples on this slide, you can see I've classified raster data sets with unique value, stretched, classified, discrete, color map, picture, and spectral. Unique values are good for raster data sets that have nominal values in which one category of cells is not more or less than the other, it's just different. And typically you have 2 to 6 classes that you're trying to symbolize. In this case, I've got deciduous or evergreen trees in Sunset Valley, and so I'm using unique value to symbolize my raster data set. We use stretched or classified symbology for numeric data sets, where you want to symbolize the raster cells on a scale that shows more or less. With stretched, you're just basically taking a color ramp and mapping the colors from the minimum value to the maximum value. In this case, it's a digital elevation model for the Sunset Valley area, and you can see that the maximum values are the highest values, and they're the lightest colors, and the minimum value are the darkest colors, and they're the lowest elevations. Classified is when you want to create some breaks so that you can actually see where hard breaks are in the data. In this case, I've taken that same digital elevation model and I've introduced about 4 breaks that show where the highlands are and then where the bottomlands are along Barton Creek. Discrete symbology is kind of a niche symbology that's utilized by professionals who don't want to apply any bias when they pick colors for their raster data set. So they'll use discrete, which randomly picks colors and applies them to the values. And you use discrete when you are looking for patterns that fall within your data. In the energy exploration industry, they'll often use discrete when they're looking at their data to see if there's some type of pattern in there that they don't expect to see. We use color map to classify raster cells when your audience is expecting a certain set of colors. For example, with land cover, we expect to see vegetation as green and water as blue and maybe built up areas as grays or reds. And so we utilize a color map to map each of the cells to a specific color palette that's tied to a particular application. When we classify picture and spectral raster data sets, there's more than one band associated with the raster data set. And so for picture, that's typically 3 bands that represent red, green, and blue. And then they're combined into a composite image that in this case is a true color image. We classify raster cells with spectral symbology when we have multiple bands, but one or more of the bands is in the non-visible light. So in this case right here, we're utilizing infrared imagery. And so we're still utilizing the red, green, and blue bands because that's visible light for us. But we've created a false color infrared where we're pushing the infrared non-visible light through the red band to create this composite image that you see on your screen. In addition to classifying raster cells with symbology, we can reclassify raster cells where we regroup cells by unique value or numeric range. One of the tools we can do that with is lookup. We use lookup to assign cell values by attribute. Now the input raster value can be numeric or text, and the tool outputs a new raster by looking up values in another field. If you look at the example on the right, you can see I've got my in raster, which is an integer raster that includes an attribute table. And the attribute table includes the category field with public, private, and federal. And then I'm utilizing the lookup geoprocessing tool to generate the output raster, which now has categorized my values by the public, private, and federal category. And if you look at the example in the in raster, you can see that values 0 and values 2 are coded as public in the category. So in the output, all of the values that were 0 and 2 in the input are now assigned a 1 and coded as public in the output. Likewise, the private values in the input are 1 and coded as 2 in the output, and the federal values are 3 in the input and coded as a 3 in the output. Now, the most common tool I use to reclassify a raster dataset is the reclassified geoprocessing tool, where we assign cell values by remap table. And this is one of those geoprocessing tools that requires your input raster dataset to have global statistics already generated. Once you have those statistics calculated, you can reclass by category or range. And you can also use this tool to reclassify no data values. Sometimes no data values actually create a problem with your ultimate analysis. And so we'll reclassify those values to 1, 0, or maybe a flag like 99. If you look at the diagram in the lower right-hand corner, you can see how reclassify works, in which you have an input base raster, a remap table, and the output raster. In this example, all of the values in the input base raster that range from 1 to 3 are reclassified as 5 in the output raster. And all of the values that range from 4 to 7, for example, are reclassified as 3 in the output raster. Also notice that I've reclassified the no data values from no data to 1 in the output raster. A couple of other approaches we use to reclassify raster cells are slice and classify. Slice is where we assign cell values by class break. And so the input raster value must be numeric, and then we can reclass the input raster by equal interval, equal area, or natural breaks. In the example on the right, I've got my input base raster, and then I've used slice 5 equal area methodology to reclass the values into my output raster. So notice that all of the values that are from 1 to 4 are reclassed as 1 in the output raster. And then all of the values that are from 5 to, say, 8 are reclassed as 2. And then notice that the number of cells that are 1, 2, 3, 4, 5, 6, 7 in the output raster is roughly equal to the number of cells in class 2, which is 1, 2, 3, 4, 5, 6, 7, 8. The last approach to reclassifying raster cells I want to discuss is classifying an orthoimagery or multispectral satellite image into a land cover data set. In this example right here, we have an input raster that happens to be a multispectral false color infrared image, and we're utilizing that to generate a land cover raster data set. Now, this is a pretty sophisticated process and something that we cover in a lot more detail in our Introduction to Raster-Based GIS class. Another way we analyze raster data are through raster queries, where we identify cell values and select cells by attribute value. Now, the query functionality for raster is not as sophisticated as it is for vector. For raster, we're really just kind of interrogating individual cells or collections of cells. For example, we can interactively query cells with the Explore pop-up tool, in which we click on a raster cell in a map and it displays the attribute values for that cell in a pop-up window. In the example on the right, I've clicked on an open water cell in Lake Travis, and you can see in the pop-up window, it gives me the count of total cells that are open water, along with the values, including the red, green, and blue values, and the class name, which is open water. We can also interactively query pixels with image information. On the image ribbon is the image information tool that you can utilize to hover over a pixel, and rather than clicking, you can just hover, and again, it'll give you the value of that particular cell. We use the image information tool more when we're working with multispectral imagery, and we want to see the value for all the bands associated with a particular location. Last, we can query integer raster attributes with select by attributes to select records and cells. So this is the select by attributes tool that we use for vector data. Integer rasters also have attribute tables, and you can use this same select by attributes tool to create an expression to select the records in the table, which will also select the corresponding cells in the map. In this example right here, I'm querying the land cover raster data set and created an expression where land cover is equal to open water, and that has selected that record in the attribute table and the corresponding 99,050 cells in the map view. And so GIS professionals often measure, classify, and query rasters to perform change detection analysis, where they classify and measure raster cells to visualize and measure change over time. We use change detection analysis to answer questions like, how has sea ice changed seasonally and annually? Is urbanization reducing agricultural lands? And how has a wildfire impacted the forest? And so we can use the analytical process, question, inform, analyze, decide, and present, to perform change detection analysis. First, we identify the question, which is to identify the change agent and impacted entities. Next, we inform our analysis by collecting and assimilating imagery for our area of interest. Then we assess our accuracy and refine our analysis to decide on our findings. And last, we present our results by quantifying and visualizing change over time.